Welcome to the Henstitute. Today what we're going to do is we're going to talk about what happens if you take a current with a magnetic field being created and pull it into a loop. So yesterday we talked about how if I have a wire, just a big long wire with some kind of current flowing through it, so I'll just call this I, that what it did is it created a magnetic field that you could use the second right-hand rule, so right-hand rule number 2, and take your fingers and curl them around this, and it would create a magnetic field that would be in this direction. So you would point your thumb upward for the direction of the current. The magnetic field lines would be curled around it like this. So this would be your magnetic field. And that's for a single wire that's just moving. And the equation we actually came up with for this is the magnetic field was equal to this permeability of free space, which is just a number, times the current that's actually flowing through this particular wire divided by 2 pi times the radius, where the radius is actually the distance from the center of the wire out to wherever that magnetic field is. So in this particular case, that would be 1 radius, and this would be a different radius. So we can, as you get farther and farther away, one of the things you notice is that your magnetic field will go down as you get farther away from that current that's actually passing. But the next idea, and that's what these pictures over here are trying to represent, is what happens if you take that wire and you curl it around in a loop. So what happens with a loop? Well, if you notice, I still have my current, so I'm going to draw that with blue here. So I have current coming out from the positive. So I'm talking about conventional current. I'm talking about the idea of positive charges moving. Is it's coming up here, it's going around this loop here, and then eventually coming back to my battery. So the direction of this loop is heading around in this direction as it's coming back to the battery. So the idea is you can see this magnetic field that's being created is actually still following the right-hand rule. So this is still the right-hand rule, number 2, where if I were to take one section and put my thumb in the direction of the current, so my thumb here is pointing in the direction of the current, and then my fingers are curling in the direction of the magnetic field here. But what you produce is you produce these little magnetic field lines that are basically going through this coil of wire. So kind of going through it in this particular direction. And what this produces is a more straight. So here over on this one, with the straight wire, you had magnetic fields going around in a circle. If you curl it around, then you get a straighter magnetic field. And then the cool part is to actually calculate that magnetic field for a loop. It's a little bit similar. So we still have the permeability of free space. So this mu is just 4 pi times 10 to the negative 7th power, and this was in Tesla meters per amp. So that's just a constant value. And we still have to multiply by the current, so that hasn't changed. But one of the things that has changed is now that we're making a loop with our wire, we don't actually have a distance away from it that we're trying to find. We're just trying to find the strength of the magnetic field. So what I'm going to do is on the bottom is I'm actually going to have a big R. This big R is actually going to be the radius of the loop. So in other words, if you make your loop with a bigger radius, you're actually going to get a weaker magnetic field. The smaller you can make that radius, the stronger the magnetic field. And then it doesn't actually have a 2 pi on the bottom because we're not talking about a circular motion going around. It just has a factor of 2 here that is related to the amount of current, because we have current going up one side and down the other. So it's kind of like a half of the current. So this is for a single loop. This is how we would actually find the magnetic field. Now, the other part of this is, what if you decided to make more than one loop? What if you had the wire actually go 1, 2, 3, 4, 5 different loops? So if you had a number of loops in here, you would actually put a big N in front of this particular equation, where this big N is the number of loops. And so we end up with another equation when we're dealing with the current carrying wire and the fact that it's going to create its own magnetic field. So we're going to play around with this equation. We're going to play around with this equation a little bit. We're going to try to do a lab that relates to this and see what we can kind of figure out. So hope that you enjoyed this edition of the Henstitute, and we'll work more on magnetic fields created by loops of wire later.